Hello everyone, so here we go with lesson 5 of the Physics 30 workbook. Really important one today because we're going to get into some conservation of momentum calculations. Just to kick things off and a reminder from class, we're going to be talking about the idea of an isolated system and then we'll eventually get on to talking about non-isolated systems. But this is a really important concept and it helps us set up a situation that we can then analyze. So we're going to first of all think about two objects that come together and collide. So if we think about object 1 and object 2, it doesn't matter whether they're both moving or one is moving or whatever, they're just going to come together and collide. So I'm just going to move the this ball number 1 and it's going to come flying towards ball number 2 and it's going to hit it. Okay, boom. The two balls collide. What we need to think about is the forces acting on this. And this will take you back to physics 20, and we're going to get into Newton's third law of equal and opposite. So ball 1 has hit ball 2, and so ball 1 is going to experience a force. Okay, we're going to call this the force that ball 2 experiences. Now, Newton's third law tells us that ball 1 will also experience a force equal and opposite. So we'll call this force 1. This is the force that ball 1 experiences as a result of it colliding with ball 2. And these forces are equal and opposite. They are going to cancel out. And so the net force on this system is going to be 0. And we're going to get thinking about the system, and I can essentially, I'll actually draw a circle around this. Oops, I don't want to do that. I want to do this. I'm going to draw a circle around it and say that this is isolated. There is nothing coming in or out. This is isolated. Okay, in other words, there's no force coming from the outside. There's no hand pushing it, so there's no force applied. That's not there. And equally, there's no force leaving the system. We're going to go ahead and assume that there's no friction. So there's no force coming out. There's no force acting on the ground from friction. So there's no forces coming in or out, which means the system is isolated. And that's really important. It's important because we can start thinking about these forces acting over a period of time. We'll remember from the impulse lesson that a force multiplied by a time, or a force that acts over a period of time, is impulse. So if we say that force 1 acts for a period of time, that's going to be equal to the force 2 acting over the same time. And so this change in momentum of 1 is going to be equal to the change in the momentum of 2. Okay, and that's really where our analysis comes from. We're going to start looking now at a linear example, and we're going to get used to analyzing before and afters and keeping track of all those momentums. So there's two things we can think about. We can talk about the idea that the total momentum initially has to equal the total momentum afterwards because this system is isolated. Nothing is coming in or out. And it depends on how many momentums we have in there, but we're going to essentially say that momentum of 1 plus the momentum of another, initial, is equal to the momentum of 1 plus the momentum of 2, final. Note that we do this little dash sign above, and that's called prime. And in momentum speak, this is really just saying final. Okay, the other thing we can talk about is this equal and opposite reaction. So just like when we were doing impulse, the two forces have to be equal to each other and cancel out, which means we have an F net of 0. If we have an F net of 0, then when we add our change in momentums, that must also equal to 0. As we mentioned before, that's our third law. Okay, so let's take a look at this example here. We need to determine the initial velocity of the 800-gram ball. So here we have a green ball. I'm actually going to call this ball number 1 just to make it easier for our annotation. This is ball number 1. That's going to be ball number 1 prime because that's afterwards. And then the red ball I'm going to call ball number 2. and there's ball number 2 prime for afterwards. So we have a before and after situation going on. I know the mass of both of the balls, and I know the initial speed and the direction, so I know the velocity, and I know the final speed of ball 1, but I only know the final speed of ball 2, and I need to find this initial speed here. So I'm going to say that the sum of the momentum total has to equal the sum of the momentum total prime, or in other words, final. Okay, so now I can just add them all together. So I've got momentum 1, I've got momentum 2, and I've got momentum 1 prime and momentum 2. Oops, I should do Roman numerals P prime. Okay, and of course momentum is equal to mv. And so I can just replace each one of these with mv. So I'm going to go mass 1 v1 plus mass 2 v2 is equal to mass 1 v1 prime plus mass 2 v2 prime. And all I need to do now is start plugging in some values here and ultimately solving for this v2 initial. So mass 1 times v1, well, my v1 is here, so this is going to give me 0.5 kilograms multiplied by 30. That's going to give me 15 kilogram meters per second, plus, well, this is what I don't know. This is my momentum 2 initial, don't know that. And then I've got mass 1 v1 final or prime plus mass 2 v2 prime. So I'm going to put these values in. This is going to be a negative value, so I'll put that in a bracket. Negative 8.5 kilogram meters per second plus a positive, because it's going to the right, 7.2 kilogram meters per second. Probably worth just mentioning that, of course, we're going to be treating this to be negative, this to be positive, so right by convention is positive. Okay, so now we just have to solve for the missing momentum, the momentum of my ball 2 initially. And so what I get is, if I get for the whole momentum, I end up getting a negative, which is good news because it's going to the left, negative 16.3 kilogram meters per second. Okay, well, let's come back to this equation over here. If I know the momentum, I can just quickly rearrange this and solve for velocity. So velocity is going to be momentum over mass. So if I take the, not prime, just velocity initial. If I take this momentum and divide it by the mass, which is 800 grams, I'm going to get 20 meters per second, and it's going to be a negative value, which tells me that it's going to the left.